Hello, everyone. The following is the third and final in a series of lectures covering Chapter 41. Today, we will be talking about the Schrödinger equation. In the same way that we could describe the total energy of an object, of a particle, of anything really in mechanics, was to find its potential energy and its kinetic energy. And even though in the world of quantum mechanics, conservation of energy still applies. So we want to take this notion of, finding the total energy of anything and that being conserved and describe it in terms of wave function, in terms of quantum mechanics. So the equivalent of, saying, oh, the gravitational potential energy of this, person on a hill and it plus their kinetic energy going downhill, has to be conserved, it's equal to the total energy, or the equivalent of, the energy of a spring block system. For a quantum particle, we can talk about the total energy of it in terms of its wave function as well as its the potential energy of the system it's in. And this leads to what's called a Schrödinger equation. So it's basically a statement about the energy of the quantum particle in terms of its wave function. And there's many forms to the equation. Since there's many forms, there's many ways to describe quantum systems and quantum particles. There's different types of wave functions. We're only going to be looking at a specific Schrödinger equation. Since we've been looking at the time-independent one-dimensional wave function, we're only going to look at the time-independent Schrödinger equation for a one-dimensional wave function. It is a mouthful, but still, you can see the equation in all its glory here. So it might not be apparent right away, but this is describing the conservation of energy. This term here includes this h bar here. This is, again, Planck's constant divided by 2 pi. So effectively, it's the constant of quantum mechanics. M is the mass of the particle. And what you have here is the second derivative of the wave function with respect to the position along the x-axis. So this whole term is an analogous to essentially the kinetic energy term in classic conservation of energy, and Ke plus U equals E. Though in classic physics, conservation kinetic energy was 1/2 mv squared. Here, it doesn't quite look like that, and that's because in classical physics, 1/2 mv squared, just talking about a simple particle. There's no consideration for wave nature duality because we really don't have to. But in the case of a quantum particle, yes, we have to consider that. So to get the full picture, 1/2 mv squared doesn't quite tell the story. So instead, we get the full picture from having this derivative here, and we're not going to have to calculate any second derivatives or anything. But what this is kind of telling you, it is telling you something about how the wave function changes throughout space. And the next term here is similar to the classic potential energy, but now we have a potential energy function. So this accounts for whatever space the particle is in, how the potential energy changes. This happens in the classic world too, right? If you go up and down a hill, your potential energy due to gravity changes, and again, times the wave function. So this term accounts for the potential energy of the environment, and this term, the wave function, accounts for the state of the particle. And then this must equal the total energy of the particle, and then the wave function here as well. So again, this is basically conservation of energy for quantum mechanics. If you were to take this and consider a big microscopic system, and you get a total energy, and then you calculate that using classical physics for like a big system, a real world thing, you will get the same result. But for small atomic particles, only this formula can tell you the full picture. You can't do 1/2 mv squared plus mgh in the world of quantum mechanics. That's not enough. Information doesn't count for uncertainty or anything like that. So we need a wave function to work with this equation. And for a wave function, for any description of a particle to be considered, legal, it must obey conservation of energy. So it must obey the Schrodinger equation. You should be able to plug in psi to both sides of the formula and have them equal each other. So the neat thing about that is that you don't have to throw equations. You don't have to throw wave functions at the Schrodinger equation to see what works. You can actually solve the Schrodinger equation to find what wave functions are allowed. The only thing is you just need to establish some knowledge about the system. So if you know what the potential energy is, and if there's boundary conditions for the system, then you can solve the Schrodinger equation and get the wave function that describes the system or just the particle. So we really kind of talked about some ground rules before for what a wave function needs to be to work to describe a real particle. So we're going to summarize them here. So the function must be normalizable, which means the particle has to be found somewhere, and the wave function basically has to drop off to zero as you head into infinity. Basically, it's saying eventually, right, the amplitude has to taper off, but it can't have infinite values either, because it's gonna it's relative probability, can't be infinite, so you must maintain infinite values in space. And the third condition says that wave functions need to be continuous. Basically, that means that you can draw the wave function without ever lifting your pen. And this is also saying that when you have different regions, with different potential energies, or maybe you have some walls or some boundaries, then the wave function can be broken down into parts, one for each region, but they all must join together. And also, this is saying that the first derivative of the wave function, much like the wave function itself, must take on finite values. You must be able to draw it without lifting your pen, and it can't have two values for the same input. Now, if we look back to the particle in the box, we can actually find the correct wave function for it by just using Schrodinger's equation. So in section 41.2, we found what the wave function had to be based on the boundary conditions. And we can just do this by looking at Schrodinger's equation and plugging in what we know. So we know that for the particle in the box, there's no potential energy inside. So the U term would be zero. So then Schrodinger's equation can be simplified. So you have a second order derivative of the wave function. And on the other side, you have a bunch of constants times the wave function. And you can, with differential calculus, which we won't do in this course, but with differential calculus, you can actually solve for what psi needs to be to satisfy this function, and you will get the same result we got in section 41.2. Another cool thing you can do is you can find the wave function for a particle in a well. So this particle is not, surrounded by infinitely high walls. This particle is kind of stuck at the bottom of the well, and doesn't seem to have enough energy, enough kinetic energy to be able to shoot up out of the well. In classical physics, right, if you have a ball at the bottom of a hole, unless you throw the ball fast enough, it won't get out. It doesn't have enough energy. In quantum mechanics, though, there's some uncertainty to the energy. So it's possible that the energy can be bigger than the potential necessary to get over the walls. So that means that it's possible for the particle to be outside the well, according to quantum mechanics. And if that's true, then that means that when you observe the particle, it's possible that you can observe it in either regions 1 and 3. In classical physics, you will only see it in this area because the particle will never have enough energy to get out of the well. But in classical mechanics, it can. So if that's true, if the particle can be found here and here, that means that the probability density isn't zero. In the particle inside the box, so here, the probability density in this side and this side was zero because the particle was stuck, because these barriers were infinitely high. But in this case, the barriers are finite, so they can be overcome in quantum physics. So the wave functions must be more than zero in this region and this region, because there is some chance, smaller than in the middle, but still some chance that you can observe the particle outside the well. And using Schrodinger's equation, we won't do the derivation, but the Schrodinger's equation, you can then find what the wave function is to describe the particle in the well. And what's cool is that you can actually find a wave function in 3 parts, one for each region. And again, because of the boundary conditions regarding the walls on the well, this leads to the wave function having levels, having quantized wavelengths and also quantized energies. So you can kind of see now that the wave function, unlike the particle in the box, it doesn't like flatten off right at the walls. There's still some amplitude here, which means that if you look at the probability density, there is some small chance that the particles will be found on top of the well in either region 1 or 2. Anyways, that's all for chapter 41, and I hope you join me next time where we will be discussing chapter 42. Thank you.